While the early transit timings were as precise as instruments would allow, the measurements were dogged by the black drop effect. When Venus begins to cross the Sun's disk, it looks smeared, not circular, which makes it difficult to establish timings. This is due to diffraction of light. The second problem is that Venus exhibits a halo of light when it is seen just outside the Sun's disk. While this showed astronomers that Venus was surrounded by a thick layer of gases refracting sunlight around it, both effects made it impossible to obtain accurate timings. But astronomers labored hard to analyze the results of these expeditions to observe Venus transits. Johann Franz Encke, director of the Berlin Observatory, finally determined a value for the AU based on all these parallax measurements. 153,340,000 kilometers, reasonably accurate for the time, that is quite close to today's value of 149,597,870 kilometers, determined by radar, which has now superseded transits and all other methods in accuracy. The AU is a cosmic measuring rod and the basis of how we scale the universe today. The parallax principle can be extended to measure the distances to the stars. If we look at a star in January, when Earth is at one point in its orbit, it will seem to be in a different position from where it appears 6 months later. Knowing the width of Earth's orbit, the parallax shift lets astronomers calculate the distance. June 2004's transit of Venus was thus more of an astronomical spectacle than a scientific important event. But such transits have paved the way for what might prove to be one of the most vital breakthroughs in a cosmos, detecting Earth-sized planets orbiting other stars.